Okay. Good morning, everyone. Just want to ask you to turn off your mic unless you want to, if you want to ask something. Okay, so I think we can continue.
Hi doctor, how are you?
Good, Alhamdulillah, how are you?
Alhamdulillah.
Okay, so I hope that you can receive the online properly, online lecture properly.
Yes.
Okay, if you could not, I will upload the recording session after the lecture finish. Usually I will do it every week, including the yesterday lecture. Okay.
Okay, doctor.
Okay. Today on afternoon, our lecturer of this class will have a meeting. So we will decide how to conduct the test, and also how to do it, whether do it on e-learning or some other way means. But well, we will let you know soon after we have decided the method and also the date for your test. I hope that you can continue completing your assignment as a Alhamdulillah that we have finished our lab or practical session before the control of movement order. Okay, I don't think the control of movement of control order will over soon, and even if after 28th of April we still have to deliver our class online or discussion online. So let us go continue with the session. Yesterday we stopped at looking at some the general type of noise. So basically there are two broad category. Number one is the external noise or the extrinsic noise. Okay, and the second one is internal noise or the intrinsic noise. So extrinsic noise come from the outside of the system, outside of the measurement system or instrumentation system, or you can say the electronic circuit. While intrinsic noise come, or the noise generated within the system, to come from inside. Okay, okay, so this figure break down the type of extrinsic and intrinsic. The extrinsic noise will basically come from outside. It can come from industry, okay, for example, the industry, okay, maybe industry, it can come from factory, it can come factory, okay. Also it can come from power lines, Hmm. So we power lines. Oh, what's going on? Power lines. Okay. Well, atmospheric it came from thunderstorm. Okay, thunderstorm, lightning, extraterrestrial. They can come from the cosmic ray, for example, cosmic rays. Okay. Industrial also you can add radio station. Okay. Ah, sorry, the my annotation keep on disappearing. But anyway, while intrinsic come from the circuit itself. Okay. Uh, like uh, from the semiconductor circuit. Okay, where we will look into the several type of noise, like short noise, transit time, flicker noise, Johnson Nyquist noise. We will look into that, and also internal like sorry, semiconductor short, transit, flicker, and thermal is not uh, noise that particularly happen in the conductor. Okay, conductor like wires and also resistors. Okay. This is the other example. Okay, industrial noise caused by human-made source. Okay, like the motor, generator. Okay, especially when you are using the AM radio, the car radio, non-digital radio, it can easily pick up the noise produced by motor or induction motor. Atmospheric noise come from the lightning, for example. Okay, thunderstorm. The thunder noise come from cosmic wave or solar flare. Okay, those okay the type of extrinsic noise or external noise. Internal noise is come from the inside the system or your electronic circuits. Okay, basically okay it depends on the function of your circuit. If your function of a circuit is to receive signal or to process signal, uh, so basically the internal noise introduced inside the receiver. Okay, so we will look into for internal noise. Okay, intrinsic noise. We look into two specific type of noise. Okay, which are the thermal noise and the semiconductor noise. Okay, so thermal, and now we go to into the thermal noise. The thermal noise is caused by random motion of free electron. So basically, free electron, when they travel inside the circuit, they do not travel in a linear motion. Okay, so basically they are moving randomly in a certain direction. So you can see they are not practicing social distancing. And during this process, due to the random motion, they will generate temperature. Okay, they generate heat, and this thermal noise is proportional to temperature. And the thermal noise, okay, this usually happen in conductor. Happen in conductor. uh, usually conductor. Conductor, okay, the wire, like so. Resistor is also a type of conductor, but a conductor with a certain resistance. Okay. So the thermal noise, okay, thermal noise sometimes is called as Johnson Nyquist, Johnson noise or Jones or Nyquist noise, or sometimes the name Johnson Nyquist combined together, it become Johnson Nyquist noise. Okay, so you can call it as thermal noise or you can call it as Johnson Nyquist noise. So as we can, we have seen from the previous slide, is generated by the fluctuation of electron that flow through inside the conductor. Okay, so the thing is that this level of noise, okay, regardless of the applied voltage, I mean the signal voltage, the noise will always happen. Okay, so though the voltage is reduced or low, noise will still it will still exhibit the thermal noise. This is the so at non-zero temperature is non-zero Kelvin temperature. Non-zero Kelvin temperature, non-zero is around 0 Kelvin. Oh, sorry. Okay. It's around 0 degree Kelvin or at negative 273 degrees Celsius. Okay, okay. Uh, so this is the temperature the electron basically they rest, they do not bounce or they do not randomly move when they flow, but above than this temperature, okay, above the non-zero Kelvin temperature, so the electrons start to jitter, okay, they start to vibrate when they move. And when they move, they basically collide with each other and then they will induce heat, okay, during uh, the move of the charge carrier, which is the electron. Uh, this means there will be a difference in electric potential between the end of the box. Okay. Uh, so basically, where as the distribution fluctuate from instant to instant, the resulting voltage will also vary unpredictably. So there will be some variation uh, from the potential, the output potential. Okay, so the output will vary, like for example in millisecond. So let's say the output is 1.2 milliseconds, so the output 1.27, some at some instant it will be 1.28, 1.29, sometimes it will be 1.30. So it will affect the uh, output electric potential. So as you can see, the noise, the thermal noise voltage, okay, can be written, can be written by this formula. This is the VRMS, okay, noise voltage of the thermal noise. Okay, so you can see here the noise level, okay, the RMS, the voltage RMS in volts, okay, is proportional to the temperature. Okay, K is the constant, but proportional to the temperature. Okay, if the heat is increased, so the noise will increase. Okay, and also proportional to the bandwidth. Bandwidth is the range, or the range of the operation range of our device. Okay, for example, the conductor, okay, your conductor, like your resistor, the operating range is between, like for example, 0 to 2000. Okay, 2000, let's say the operation range is 0 to 2000. Okay, so the bandwidth is will be, okay, the bandwidth, let's say the operating frequency, eh, it, eh, frequency, so the frequency is 0 to 1000, 1000 hertz. So the bandwidth will be 1000 minus 0 will be 100 hertz, 1000 hertz. Hang okay. And R is the nominal resistance of your conductor. Okay, if in the case of the conductor is a resistor, so if the resistance value is high, so the RMS noise, RMS noise voltage will be high. Okay, so one way how to reduce, okay, to reduce this thermal noise, okay, is to cool down the circuit. Okay, cool down the circuit. The temperature will cool down the circuit due to the motion, okay, of the electrons. It cause the vibration, it cause collide each other, it create the heat. So how to reduce this noise is by cooling down the circuit. That's why in certain circuit you can see they have the fan, okay, to push out the heat, okay, out from the circuit or from the box. So this is one way how to reduce the uh, to reduce the RMS voice voltage. Okay,
Doctor, again, please this point.
pardon?
Uh, can you repeat this point again, please?
This slide?
How can I reduce? How can I reduce the noise?
Oh yeah, yeah. Okay. So how to reduce the RMS voltage noise is by cooling down the circuit. Okay, cooling down the circuit. Okay, so how to cool down your circuit? Okay, your circuit, okay, maybe uh, place inside a box or container, okay, for safety issue. So you can install a fan. Okay, you install a fan to purge out the heat, okay, the heat out from the box to cool down the circuit. So that's one way how to reduce the RMS noise voltage. Okay,
I just reduce the temperature.
Yeah, the temperature. Reduce the
Yeah,
temperature.
okay, thank you.
Okay. Other factor like bandwidth, pretty much this is this if you want to reduce the bandwidth, okay, this is pretty much the setting or the design of your device or your conductor. So bandwidth, okay, resistance pretty much there's not much you can change, but definitely how to reduce, you can cool down the temperature. Okay. Right. Uh, right. So that is thermal noise. So thermal noise happen, like I explained, it happen in conductors. Okay, conductors. Okay, for example, in wire and also in resistor, they are both conductor. For wire they in ideally they are basically 0 ohm, but there's no basically they actually have some degree of resistance, but very small and negligible. But they do actually exhibit some noise. And now we see into the type of noise. Okay, semiconductor noise. Okay, so this is the intrinsic noise, okay, coming from semiconductor device, especially in like transistor, diode. Okay, so we will look into some the example of short noise, transit time noise, and also flicker noise. Okay, the short noise is basically the consequences of charge being quantized. Okay, this is due to DC electrical current. Okay, DC electrical current. Okay, uh, basically short noise in electronic device result from unavoided random statistical fluctuation of electric current. Okay, when the charge carrier, so in this case we have charge carrier inside a semiconductor. Charge carrier, if you can remember, charge carrier can be electron and can be holes. So if electron, the charge carrier is negative, holes is positive, right? Okay. So basically what happens, so the charge carrier, okay, when in semiconductor, when you apply a voltage, it will transverse, okay, through a gap, okay, a gap or a barrier between the semiconductor. So let's say we have Pn. So when there's Pn, there is a barrier here, okay. So basically the electron flow across this barrier, okay. When they travel or they pass through the barrier, they have discrete time arrival. They have discrete time arrival time of arrival. Okay, and those discrete arrivals exhibit short noise. Okay, the process when they try to travel or jump through the barrier, okay, they what we can there is what we call as discrete arrival time. Okay, discrete arrival time. So during this process, okay, it will create noise. Okay, then this noise is called as the variation of current, delta I. Okay, yeah, okay, delta I. Okay, and in electric, this fluctuation we can quantize it by using a formula. And then, uh, Okay, delta I equivalent to, sorry, I cannot choose the to the oh sorry, I delta B, okay, OB, sorry, let me rewrite it down, OB. Okay, so this is the random variation of current. Okay, this we quantify the short noise. Okay, which you can see. Okay, short noise is the square root. Okay, the variation of current is square root of 2 multiplied with E is the elementary charge value. Okay, for electron. Okay, you can find it's a constant. So E is a constant. Okay, constant. Constant. Okay, and I is a DC current. DC current. And B is the bandwidth. Okay, bandwidth. Okay, the bandwidth operating bandwidth. Okay, so remember that in semiconductor, when we bias the device, we use DC voltage. Okay, but the device actually process AC signal. Okay, AC signal. So the short noise is proportional to the DC bias current and also proportional to the bandwidth. Okay, so how to reduce? Okay, one way to reduce it, okay, by carefully choose the optimum level of DC biasing and also using a bandwidth filter. Bandwidth filter means that you operate, okay, the device at a gap, very a narrow gap of frequency. Okay. Okay, transit time noise similar to short noise. Is similar to short noise due to the variation of similar to transit noise. Okay, similar in term of the variation of current. Okay, delta I. But the thing is that transit time noise. Remember that when the charge, okay, the carrier, okay, move across the barrier, it has its discrete time arrival. Okay, discrete arrival time. So when the discrete uh, arrival time is equal to the signal frequency, okay, then transit time noise will come into the picture. Okay, will come into the picture. Okay, so remember that remember if in electronic, if you still remember in electronic one, okay, you can use your semiconductor device like transistor, okay, transistor, or you can also use diode, okay, diode to process signal. For example, diode you can use as a you can use to clip signal. For example, if you use diode to remove, if you have AC signal, you can use it to remove the negative part. Okay, or in transistor, you can use it as an amplifier. Okay, you can amplify signal. Okay, you bias the transistor and can you inject the signal through the base gate, and then you can amplify the signal. For example, but the signal, when the signal frequency that we want to process similar or the same to the time arrival. Okay, the discrete arrival time value. Discrete arrival time is 1 over t, so you get the frequency of the uh, discrete arrival time. So when the frequency match, so transit time noise will come into the picture. So it is very important, okay, in this to limit, okay, to limit the operating frequency of your device, means that you have to apply a, a, a filter or bandwidth filter, okay. So you can use for example, low pass filter. Okay, low pass means that you cut off the high frequency. Okay, that's why it's called as low pass filter. You can use a low pass filter. So you avoid from signal is very high signal to process by to through your semiconductor device. So that is called a transit time noise. Okay, flicker noise. Okay, transit time we have the that's flicker noise. Okay, result from the variation of resistance. Okay, resistance. So transit time noise, short noise, or variation of current. Flickers noise result in the variation of resistance in semiconductor device. So uh, the flicker noise is inversely proportional. That's why it's called as 1 over f frequency of pink noise. So as the frequency increase, this noise will decrease. Okay. So it's also can also be found in resistor and conductor. Okay, not other than semiconductor. This is due to the impurity of the material. Okay, impurity means that when during the process, the doping process. Okay, if you like let's say you make a semiconductor during the doping process, so there is a chance where there are some impurity will come into the process. Okay, that will cause the fluctuation of resistance in the device. Okay, so this if you buy some component, so you can find from the data sheet. Okay, the specification, the noise range. For example, if you buy carbon composition resistor, the range it basically is small, 0.1 microvolt, but depending on the type of application that you want to use. So like for example, if you want to create a device for example, signal processing, you want to use it for EKG circuit or device uh, that measure or the process very weak signal body, human body signal or human organ signal or electrical signal and want to amplify. So you have to take into consideration the noise level of each of your component. Okay, each of your component. Okay, so this table this picture basically compress all the type of semiconductor. Okay, semiconductor noise. Okay, so we have here 1 over f. Okay, is the flicker noise, okay, or the ping noise. Okay, and then we have a thermal and short noise. So basically thermal and short noise, they are thermal noise or short noise, basically they are uh, also what is called as white noise. Okay, this is white noise in semiconductor. Okay, white noise. And basically I think this figure need, so for thermal noise or okay or short noise, basically the noise occupy all frequency available, all frequency uh, bandwidth available. So the level of thermal noise will be at every operating frequency. Okay, so you see the equation where it is proportional to the temperature, proportional to the bandwidth. Okay, but transit time noise, okay, proportional, okay, to the bandwidth, okay, and also proportional to the current, okay, if you still remember from the previous slide. Okay, this is other type of noise. It's called as burst noise. So they are basically random. This is called as random noise. It could happen in, okay, at any instant. Okay, just random. Okay, so and then also this type of noise it lasts only a very small fraction of time, like millisecond. Okay, so it is the random. They also very I mean one of the type that random in terms of the occurrence at a certain frequency. Okay, avalanche noise. Okay, this is noise where when breakdown. Okay, the breakdown of the semiconductor device. Okay, semiconductor device. So you remember the principle in semiconductor when you apply DC current across a semiconductor device, let's say Pn, so there will be a boundary. Okay, so when you further increase the voltage, so this depletion region will be bigger, okay, larger. At a certain point, it will break down. Okay, during that breakdown, okay, it will produce what noise, what they call as avalanche noise. Okay, white noise. You remember, okay, in white noise, that thermal noise or junction increase noise is categorized as white noise. Okay, why? Because the signal, okay, contain equal power within a fixed bandwidth. Means that this signal or the noise will occupy all the frequency bandwidth available. Okay, so there will be at any point of the frequency. Okay, that's why it is called as white noise. Okay, so this is the figure showing how the level of white noise, okay, from 1000 or from 100 to beyond 10,000 hertz. So the intensity level, okay, is constant. Prac- uh, Practically constant. Okay, so also, okay, this white noise, okay, we can experience from the environment. Okay, from the environment. So in our environment also, there are white noise. Okay, simple example that you can experience this white noise is by you pressing your, okay, you uh, flip your ears towards to the front, and then you press with your with your hands. Okay, and then you just sit down calmly in a quiet room, and then you can listen the sound, the background sound, that is a white noise. And also when you uh, going or in on a flight, on an airplane, okay, when everyone is like already settled down in the airplane and want to sleep, and then you can hear the background noise, right? So those are also white noise. Okay, okay, like for example the cricket noise, they also white noise. Okay, hair dryer, they are also white noise. Okay, and TV static. Okay, TV static, if you still have that analog TV, so these are white noise. Okay, but it has an adverse effect to human. Basically, if we expose too much, okay, like cricket, okay, it's okay, it's relaxing, okay, but like TV static, okay, if you sit down in an empty room and then you have this analog TV with the TV static, and then you sit there for a long time, okay, actually at a certain point you will go insane. Okay, So it has a adverse effect to our human, maybe human psychology or human state of mind. Okay. Okay. So there are other type of noise. Okay, like natural source of noise, cosmic ray. Okay, circuit noise, thermal noise we have discussed, and also man-made noise. This is basically induced noise. Okay, induced noise, man-made noise. Okay, so how do we measure noise? We quantify noise on a signal. We use what we call as the noise or signal to noise ratio, S S/N ratio or SNR, signal to noise ratio. Okay, so what does this signal to noise ratio tell us is that the strong signal, okay, strong signal and a weak noise result in a high SN ratio. Okay, SN ratio. So it means that if our signal is high, okay, and then our noise is low, so we have a high value of signal to ratio, which is good. Okay, a weak signal, a strong noise result a low signal SN ratio. So this is not good. For example, okay, signal without noise is basically the level of noise is 0 dB. Okay, 0 dB. Meaning that the noise level is 0. Okay. But when let's say we have signal, original signal, and then contain some noise, and then we measure the signal to noise ratio, we get 20 dB. So this 20 dB is high, okay, high, okay, acceptably high. So the signal is good. Uh, uh, it has its original form, but contains some signal. But when the SN ratio go down, okay, like 10 dB we get here, so they contain a lot of noise. Yes. So basically, this noise is enveloped inside the signal, the original signal. So how to measure can be expressed in terms of the power or voltage. Okay. So we can use the SNN to S over N equal to the Vs, signal voltage RMS, divided by the noise voltage RMS. Okay, I think this is basically it should be, you know, uh, it should be square. Okay. Okay. Oh, sorry, no. This is correct, but this is already in RMS. Okay, or RMS. But if our signal is in the estimated signal value, I mean the amplitude, so we have to square the signal and divide the unwanted signal of the noise square. Okay, okay, this we can use this equation, okay, to find the signal to noise ratio. This is in term of a 2D image. Okay, it's calculated by, okay, each pixel it has its own uh, value. Okay, contrast, for example, contrast value. Okay, so if let's say this is comparison between different quality of figures in 2D image. So signal noise ratio in image we calculate pixel by pixel. Okay, pixel by pixel. Okay, and then we find the effective value of the total pixels. Okay, total all pixels we find the effective value. So, for example, in the A figure, okay, signal to noise ratio in the total is 23, meaning that you can see the actual figure or the object figure is highlighted as compared to the background. So we get the high signal to ratio value. As B, we have low. So we can see the figure, the object that we want to see as is starting to blend with the background. Okay, so as the signal to ratio go down, so for example D, this is figure very low signal to noise ratio. Okay, due to the high effect of the background to the object or to the subject that we want to uh, capture. Okay, we want to image. Okay, so how we calculate? So this is an example. The signal to the to ratio. The equation is a voltage of 10 volts. Okay, 10 microvolt is amplified using a transistor amplifier, so that the output is 100 millivolt. Okay, so input is 10 microvolt. So we have a amplifier which is using a transistor amplifier, and then we have the output 100 millivolt, and then there is a noise introduced into the original signal, and then the noise level is given as 15 microvolt, okay, which is generated by the amplifier. Okay, this may be due to uh, due to the short noise. Okay, remember the short noise because of the variation of current, DC current. So remember when we use transistor, we have to bias. Okay, we have to give a DC bias. And once we have the DC bias, there will be some short noise. Okay, and in this case, okay, the noise level is 15 microvolts. So what is the signal to noise ratio at output signal? So we simply use the formula. So our signal, the output, okay, signal is 100 millivolts. Okay, and then volt square divided by the 15 microvolt. So we have 44.5 mega. Okay, mega, 44.5 mega. So signal to noise ratio, if we take directly the ratio, there is no dimension. Okay, but we can calculate the dB value, the decibel value, by using the log, okay, log log function. So in this example, the signal is 44.5 mega times higher than the noise. Okay, 44.5 mega times. So therefore, in this case, we can say the noise can be, visually the noise can be neglected. Okay. Okay. Then let's see at the next example.
Doctor, I have a question.
Yes.
When we should put a square and when we should not?
If we are given the amplitude, or if not stated, that is actually the amplitude of the signal. Okay. But
Okay.
if we are given the RMS value, no need to square.
So that means other than the RMS value, we have to square.
Other than RMS. Like for example, this question does not stated whether RMS or not RMS. But if not stated, this is the amplitude. The amplitude. The amplitude. Okay. This is the amplitude. So like 10 microvolts, so the amplitude. Okay, and then the output is 100 millivolts, so that is the amplitude.
Okay, thank you, doctor.
All right. So how do we calculate? This is another example. We have two different types of amplifier. We have amplifier A and then we have amplifier B. So the input voltage or the amplitude voltage of for A is 25 millivolts. Okay, and then the output voltage is 1 volt, and then the noise level, okay, is 10 millivolts. While amplifier B, okay, the input voltage is 1 microvolt, very small, and then the output is 30 millivolts, but the noise level is 25 millivolts. Okay, so we can say that A and B are sound amplifier, amplify the amplitude. Okay, amplitude. So basically, this is we are having the amplitude of the sound in voltage. So calculate the signal to noise ratio of the amplifier A and B respectively, and we have to determine which of the amplifier will produce a better quality of the sound. Okay, so we use the formula. For amplifier A is digital signal square divided by the noise square, we get around 10k. While for amplifier B, okay, the signal square divided by the noise square, we get 1.44. So we can conclude here for A amplifier A, it has higher signal to noise ratio as compared to B. So therefore, amplifier A will basically produce better sound quality than amplifier B. So because amplifier B, okay, the output sound, okay, will basically distorted by the noise. So remember, noise, the level will be not random at a certain frequency will be random. So basically for amplifier B, the quality of the sound will not be good. Okay, so this is the noise mechanism. Okay, so we put the input the signal. So we have the amplifier. Remember, we have the power source amplification in electronics, and then the output. Okay, and then basically input has no noise, but amplifier has power source. Okay, signal. Output will basically envelop the will contain the input signal and the noise. So the noise can be generated by the external or internal. Okay, remember that if we use like for example as transistor, okay, circuit, okay, amplifier circuit will contain not only the transistor, also will contain the conductor. Okay, in case of conductor, including the resistors. Okay, resistor. So so that will also introduce noise into the amplifier. Okay, okay, so that noise will be compounded, okay, into the circuit, and then will be enveloped into the input signal. Okay, and remember that it also include the intrinsic noise, like short noise, okay, avalanche noise, or burst noise. Okay, but burst noise is random. Avalanche, if only we bias the too high, but short noise, okay, is due to the variation of the current. Yes, so they also affect the contribute to the noise, uh, the induced noise into the input signal. Okay, all right. So if you want to well to if any if you want to design any amplifier circuit, basically you have to evaluate the noise characteristic. Okay, for example, uh, okay, in amplification, not only you can use a transistor, you can also use a op amp as an amplifier. So if you want to know the performance of your device, like for example, or op amp, okay, you have to look at the data sheet. Okay, like op amp, okay, they have that signal to noise ratio level, so you can look into that. But usually, choosing the right op amp depend on the application. Okay, for example, if you want to use it for sound amplification, so basically sound is basically you amplify the electrical signal coming out from a microphone. So the signal is basically the source of the signal is connected directly to the amplifier. But other signal, like for example human body okay, human body electrical signal like EKG, ECG, or uh, brainwave. So those are very weak signals. So they are specialized op amp, like for example instrumentation amplifier. So you have to choose a very uh, special op amp that have a very low signal to noise ratio. Okay. So this I have explained in the previous in the beginning of the class, okay, how to reduce the junction noise or the thermal noise. Okay, basically we reduce the ambient temperature. Okay, uh, basically we have to reduce. Okay, we have to reduce or to avoid any uh, for example, the ambient temperature, like our surrounding temperature is humid and very hot, so we have to carefully put our circuit inside a box that does not expose to the ambient temperature or our surrounding temperature. Okay. So that is one way is use the method how to reduce the temperature and also improve, okay, junction and increase the thermal noise in the design process. Okay, design process, you can use the special material, okay, special material to the resistor. Okay, basically this special material avoid or stop the device or the resistor, for example, from overheating. Okay, for example, this special film actually this help the temperature to be dispersed or to be transferred efficiently from the transistor or from the resistor itself to the surrounding or to the air. Okay, shielding or filtering is not effective. Okay, remember that this thermal noise is the V, uh, the RMS, okay, voltage, okay, the RMS noise, thermal noise, okay, proportional to the temperature, proportional to the bandwidth, okay, frequency or the operating frequency. Okay. While white noise, okay, like the short noise, okay, or other type of noise, like including the background noise. Okay, so how to reduce for, okay, uh, remember that the white noise, okay, this is due to the variation of current. Okay, so you can use we can carefully select the bias, current bias, okay, the current bias level, and also okay, uh, maybe uh, maybe and also use some filter, okay, because short noise is a type of not white noise. Okay, remember, okay, basically white, in this case white noise and short noise are the same category. Okay, short noise, because short noise is occupy all the bandwidth frequency available. Okay, so one was to use a filter, meaning limit the bandwidth. Okay, limit the bandwidth of the operating frequency. And other noise coming from the external, for example, electrical appliances. Okay, electrical appliances like our blender, for example. Okay, for like other uh, very high frequency devices lah. Okay, so you can use filter, okay, to reduce the effect of the electrical appliances. Okay, harmonic noise, okay, noise 60 hertz. This is basically, for example, coming from transmission line, okay, power line. So basically our frequency, the frequency for our transmission line is around 50 hertz. So how to reduce the effect of this noise is by using appropriate filter or using a shielding. Shielding meaning that if you have a device, so unavoidably you place this device close to a transmission line. So how to reduce the effect of the from the device from the transmission line is using a shielding. So how shielding can be done? Okay, for example, by using a box, a conductor box like aluminum box. Okay, like aluminum box. Okay, for example, aluminum box. So you place your device inside the box, and then this box is basically grounded. Okay, grounded. Okay, wire to the ground. So any interference, okay, coming from the, for example, the transmission line, okay, will induce on the surface of the uh, metal, for example, aluminium, anything that will induce on the on the surface will go down to the ground. Okay, so this one way how to reduce what is called as the harmonic noise. Okay, like motor, okay, how, okay, like our generator, sometimes you have the independent power, small power generator using diesel or petrol or fuel. Okay, especially when you go to the night market, so the stall they are using this type of generator to create a lot of noise. So how to reduce the noise coming from this uh, mm, device is by grounding. Okay, grounding, for example, grounding the cover of the device, and then shield the terminal wire like the same like before. Okay, and also maintain, okay, the generator, okay, periodically. Okay, for basically generator, they are basically have um, stator and rotor, and the thing that connect between the stator and rotor, there's a brush, okay, brush that maintain the connection, okay, that will make sure the rotor, okay, will turn and then make contact with the stator. So you need to make sure the brush is in good condition, because the brush, the contact will deteriorate or will wear down over the time. So if it wear down, so it will create a lot of friction, so it will induce a lot of static noise. So we need to service it periodically. And also we can use the shunt capacitor, the shunt capacitor at the brush motor. So how the shunt capacitor work? Okay, basically we capture the static noise. Okay, the static noise. The static noise basically capture the current, and then it will discharge it slowly to the ground. Okay, and also using a feedback capacitor. Okay, a similar concept, but feedback capacitor will directly send back the current to the terminal. I mean, this is not terrible. I mean. Anyway, the other frequency generator like our radio or walkie-talkie or other radio transmitting device. Okay, so to reduce, you use a cover on the device, but only let the antenna go out. Okay, then other type using shunt filter and also a silent trap to a specified frequency. So don't worry. However, you can search what is silent traps. Others like relays. Okay, relays. This device relays is basically in the industry. Okay, the purpose of controlling relays is to isolate between the control signal and the high voltage signal. For example, our street lights. Okay, our street light they have relays. Okay, the relays that connect or close the high voltage signal, that turn on the light. But relays, okay, basically is the device that isolate between the control signal and the main voltage line. So when the relay okay is switched on or operate, basically it will create a surge current. So basically when the contact is closed during the process, okay, there will be some spark okay between the connector. Okay, so how to reduce this spark is by introducing a capacitor. So basically the capacitor will cut off the transient. Okay, transient. So during the so when the contact is open, basically the voltage is zero. When it is immediately closed, so there will be a sudden increase. So if there is no capacitor, so the increase will go over the nominal value. Okay, the spike probably will go over the nominal value. Like say for example, 200 volt, it will go more than 200 volts. Okay, so to reduce that spike or the transient sudden transient change, so we use a capacitor to limit or to reduce the transient response. Okay, other noise reducing technique, if you are using A to DC converter or digital to analog converter, so this is especially in signal conditioning. The signal conditioning where we want to have an interface, okay, between device to our microcontroller or controller, for example. So ADC is a device that is used to translate the signal of our device to our microcontroller. Okay, so how to reduce the signal by creating a shield on the unit, so avoid any signals coming from outside introduced into our system. And also we can use low pass filter on all wires passing through the shield. Okay, low pass filter you can use the passive low pass filter. Okay, or passive low pass filter basically it consists of wait, um, uh, let me check. Okay, passive low pass filter basically is just use a resistor and a capacitor. So this is our input. Okay. So this is our output. You can use a passive low pass filter using a resistor and a capacitor. So tau is equivalent to RC, okay, and the frequency, cut-off frequency is over 1 over tau, okay, or 1 over, meaning that, for example, okay, if this is a low pass mean that we, okay, gain, okay, sorry, gain, and the frequency, okay, frequency, so it will only allow low signal, okay, low level, okay, anything that is below f, okay, the cut-off frequency, this is the cut-off frequency, okay, cut-off frequency, yeah, cut-off frequency, anything below the cut-off frequency will be permitted, okay, above it will remove, okay. So one way you can use what is called as the passive low pass filter. Other than that, like electromechanical vibrator, you can this is, I think, you can read. I don't need to go one by one. But one important thing I want to share or want to discuss, tell you, is about the EMC, or the electromagnetic compatibility, and the code is EMC C89 or /236/EEC. Okay, this is basically set all manufacturer to comply with the EMC compatibility, or electromagnetic compatibility. So the definition, okay, basically tells you that any device should function without causing any interference to other tools and also itself, okay, and also that your device should not be harassed, should not be affected by other sources, okay. So because, okay, this is very important, okay. For example, you can see at the back of your phone, where there is a EMC or EMI certification. Okay, so especially this kind of device like TV, motors, okay, your phone, your smartphone, your computer, any electronic device must comply with, okay, must have that EMI certification. Otherwise, okay, it will basically interfere, and also it will mean when it operates, it will interfere with other devices. Okay, so we look into the some case study. Okay, for example, okay, in automation, in some factory, we cannot avoid using automation. For example, in the foundry plant, where involve the process of melting steel, okay, moving the molten, okay, the molten steel from one point to another point from the furnace, moved on into the mold, okay. So in this case, there's a case, an accident, okay, the foundry worker died because the radio control overhead transporter, basically the transporter, it carry the molten steel, okay, molten steel. It was supposed to pour into the mold, okay, when it arrived at the destination. But in this case, what happened? There's a malfunction, okay, because the radio control overhead transporter that carry the molten steel accidentally triggered to to purge out the steel during the transportation. Okay, this is because the signal from the radio transmitter was interpreted by the automatic system. Okay, so there is a there is a noise or there is a faulty signal. Okay, so this can be avoided, okay, by, okay, make sure the radio control overhead transporter immune to any noise. So, or maybe what we can do, we install a fail-safe system where, okay, it can only be I mean the pot we can only be moved when it reach at the destination. So there's a fail-safe. We can use a fail-safe system. Yeah. Otherwise, the pot, okay, cannot be turned over uh, unless it is reach at this destination. So then in some very critical process, okay, there should be a balance between automation and manual. Okay, some process must have a human intervention. Okay, it cannot be full, and some process cannot be fully automated. Okay, and in other case, okay, burning crane. Okay, so a worker was burned down when he touched the load of a crane installed for a building of operation. So basically, a crane. Okay, so a crane basically a tower, a conductor, a metal tower or aluminum tower. It consists of basically consists of the stainless tower and connected to a cable. So basically, they are all conductor. Okay, all conductor. So in this case, so what happened? It becomes the tower. Okay, it become a big antenna. Okay, a big antenna. So when there is a nearby broadcasting transmitter, broadcasting transmitter transmit Wi-Fi signal, for example, or wireless signal that carry high level of power. So the tower becomes a receiver. Okay, the surface becomes a receiver. So basically, when you have a conductor surface, okay, conductor surface, it basically there will be induced current, circular current on the surface. So that induced current will accumulate on the surface. The larger the conductor surface, the higher the induced current. So this is the induced current basically it trapped on the surface. So when this and also it called as the static current, okay, induced and accumulate on the surface. So when a worker touch one part of the crane, so what happened? All the current that is induced on the crane on the surface will immediately uh, transfer or flow to the worker and then terminate to the ground. So it want to, it want to discharge. So during that process, all that high induced current will go through the worker, and basically it didn't the worker didn't die from the heat. Actually, it died from the electrocution from the current flow. So basically, that current will stop interrupt the heart motion. Okay, basically they stop the heart, and then in the same time, when there's a high volume of high level of current, okay, flow through human body, they will induce heat. Okay, similar like that if someone or anything that is uh, hit by thunder or lightning, so there is a very high current. So in the same time, okay, when thunder hit, for example, a tree, it will cause fire. Okay, fire because of the heat. Okay, due to the current. flow. Okay, and other process like ABS failure. Okay, ABS, we have an electronic device which control electronic system which control the braking system. Okay, they are very sensitive and then very susceptible to electronic interference. So it must be tested and must be certified not to disrupted by electronic interference. So there are cases where there are ABS failure where it receive um, fail signal due to the electromagnetic interference and causing the when the car is moving, okay, at the high speed, causing the wheel to lock suddenly, and then the driver will lose control of the car and then cause fatal accidents. Okay, and then also this other example, a black hole in railway system. Okay, this is due to the lost data, okay, lost information. Okay, uh, because of the interference from outside. Okay, because the radar station with um, the radar station that emits high radiation, okay, we will cause the uh, automatic train registration system to lose the signal. Okay, I think other than that you can see. So there are negative impact of electromagnetic interference. I cannot open that. Okay, also like drill machine. Okay, especially you can hear from your uh, from your smartphone, for example, when you are in the middle of an important call. So there's someone using a high power drill, for example, hydrogen machine. It will cause an interference, and then also it will interfere with your call. So designing an EM the system, designing a system, basically it must comply with the EMC test. Okay. During the EMC test, you must basically anticipate. Okay, in the design process. Okay, for example, you have must anticipate the possible source that can interfere with your device, and also uh, how your device can interfere with other devices, and also how the parts, okay, the parts in your device, okay, between one module, okay, your device can be many modules, so you have to check every module starting from the power supply to the main the important components. So we have to test the compatibility, and then during the electromagnetic compatibility, there must be a lot of tests. Okay, in Malaysia, usually the electromagnetic compatibility test is conducted by the certified lab body. Like in Malaysia, they have this SIRIM. SIRIM is a body that tests all equipment, electronic equipment. Okay, they will send for certification. Okay, and then they will can have certification, official certification. I think this is the last slide. Okay, this is, I think, the information you can read by yourself. There's nothing that implicit about this information. Okay, uh, so I hope that everyone uh, have no big issues, okay, attending the class. And if you have any issue, you can WhatsApp And also, I will announce later. Okay, test one, test one, test one. Basically, we will have a discussion with other lecturer. Okay, this afternoon, this evening. Okay, so after this evening, I will let everyone know if we have decided when we will conduct the test one. Okay.
Doctor,
Yes.
please, Doctor, could you make a revision for on the first four a revision on the first four chapters? Could you make a revision?
You mean
Or,
you want me to deliver the online course for the first four? So I think the best thing is
yeah,
that
I ask you if you can make a revision on the first four
uh,
chapters for us.
that is as good as I begin the
What?
no, that is like I begin the class from the beginning, but because I have already delivered that class okay, face to face. But what I can do is that we after this class is over, what we can do, we do revision. Okay, we do revision. Okay, for example, we do some final equation regarding chapter 1, chapter 2, and so on. Okay, that would be better lah. To focus on the, I indirectly repeat the earlier chapter through the exam question. So I think that would be better.
Yeah, okay. Thank you.
Okay, so I think again, thank you everyone for coming, attending the class today. Uh, so, inshallah, we will continue our class next week. So, with that, I conclude our class for today. Thank you very much.